Okay, our last talk for this session is by Josselin about a multiverse type theory.
Thank you very much. I'd like to thank the organizer as well for organizing this nice event. The organizers, sorry. So I'd like to talk about a multiverse type theory. So maybe I oversold it a bit on the abstract, but this it's not actually a concrete type theory, but what we would like to do and what kind of problems we identify and what we are trying to work on to resolve those. So first I'm gonna try to state the why of this project. So basically we've kind of seen a lot of new type theories which got developed to solve some domain-specific problems. And it's really nice that we have all those different type theories because they let us solve problems in a concise way. But the issue is that they're all in their own bubbles. So I got a lot of examples for this. So for example, we have Martin-Löf type theory with S-prop. We have exceptions because we might want to talk about exceptions. We have cubicle type theory, which is one big example of this. For example, in Agda, you have two different standard libraries, one for cubicle and one for non-cubicle, and they don't really let you talk to each other that much. But we might also want a type theory where we have also an internal language for pre-sheaves and a way to go from the internal language to the external language. There's no reference because I don't really know of any work on such a type theory yet, but maybe I've been missing some. There's also two-level type theory. And finally, something that we saw with Joris' talk, guarded type theory. And next talk, we're also going to see yet another type theory. So we keep piling them on, and maybe there's no end to them, and maybe we would like to have them all talk to each other in a single unified system. So let me just give you a rundown of two basic examples I'm going to use throughout the talk to highlight the main problems we might have. So in MLTT plus S-prop, basically we have two universes, one of types and one of proof irrelevant propositions. So we have basically the most important rule in that system is that for any type in S-prop, any two elements, any two terms of that type are definitionally equal. So this is really useful because you might want to not care anymore about proving that things keep being equal, or you just don't care about the proof, basically. And what we can do is we can also talk between the two universes by squashing types. So if I have a type, I can just say, I don't care about the terms of that type. I can squash the type and put it in S-prop. So this is really nice. But for example, if I squash the booleans, then the booleans, well, squash of true is equal to squash of false. So what happens is that I cannot eliminate from the squash of bool into type in the usual way. I cannot just say, yeah, true, I'm going to eliminate true to something and false to something, because those two things will have to be definitionally equal for it to work. So that means that we don't have the usual elimination principles we're used to. We have some restrictions. And only bottom enjoys an elimination principle into type, basically. But from S-prop to S-prop, it's fine because everything is equal, so we're not going to have the same troubles as I highlighted before. The other example is exceptional type theory. So I'm taking a very simplified version of what you can find in Pierre-Marie Pedro and Nicolas Tabarros's papers. But basically you have another universe, which is the universe of exceptional types this time. And there, basically every type is inhabited by an exception. And what that means is that I can take a usual pure type and just say, oh, so I want to consider possibly exceptional values of that type. And so the same as I can squash a type, I can put a type from the type universe into the exceptional universe. And the thing is here, again, if we want to eliminate values of the exceptional type into the exceptional types into type, what we need to do is handle this extra value, which is the exception, with a new eliminator, which is basically just try catch. And so here we can still see that there's some difficulties with finding the right elimination rules. So here we are going to have this elimination principle for all of these types. But as we saw before, for example, for S-prop, we don't have this kind of elimination rule for all of the squash types. So yeah, most of the type systems I alluded to in the introduction, they combine multiple universes of types that behave differently. So for example, MLTT plus S-prop or MLTT plus exceptional types. And the reason for that is that we can keep the pristine type universe and add whatever bunch of weird rules we want in another universe. As long as we can control how those two universes interact, we can keep the nice properties of the type universe. So for example, in the exceptional types, bottom has a term, so consistency does not really hold there, but because we cannot eliminate from bottom exceptional to bottom in type, because that would require handling raise, and we cannot find an actual term of type bottom, consistency will still be guaranteed. So that's, I think, the most important part of why we use different universes. But we might also want certain universes for things more general than just having MLTT with some more properties. For example, in cubical AGDA, we have I, which is not a usual type, it just lives in its own universe. And that's really useful because I, since it's isolated from the rest of the system, provability of formulas in I is decidable, and that's one of the main properties that we need for cubical to work and to compute. So here again, we see that isolation is really important. So yeah, if you want to use any of those type systems, well, you have to think beforehand of what kind of features you want, and you'll have to stick with a single meta theory. And that's kind of a problem, and usually we call that vendor lock-in, and it's seen as a bad thing. It depends on, I mean, I saw a lot of Apple computers in the room, but personally, I'm not a big fan of vendor lock-in. So we kind of want to resolve this situation with a multiverse type theory where we could combine all of those theories together, but it's kind of a very ambitious thing. So this is more going to be a survey of what we think of the outline of the problem and what we can bring to the table. And so if there's something that either you don't agree with or that you might have some answer to, you can, of course, interact with me during the talk. I'd love to have some feedback on those. So I think first we kind of need a structural framework to be able to fit all of those systems inside a nice single unified structural framework. So we kind of have two options. There's a weird PTA style attempt with basically it's a type theory that's inspired by what actually happens with ROC, where you have type, prop, and now S-prop. And so there was kind of an attempt at formalizing this with a paper, unpublished attempt presented here 2 years ago. But there's also multimodal type theory, which you might be familiar with from yesterday. So I'm going to first compare a bit both of them and explain what advantages and disadvantages they have in comparison. So we kind of have similar judgments saying that we have different sorts or different modes. So this is going to be basically the universes. And the first divergence between the two systems is that in multiverse type theory, you have contexts living in the void, whereas in multimodal type theory, contexts live at a specific mode. So this is, I think, the main difference between the two systems that are going to make them diverge and is going to cause down the line some differences. We have very similar statements, just different grammar syntax, but types live at a specific mode or sort. And then here we have basically the same judgment, but here I kept the @m because that's how it's usually presented. And one of the main differences then comes into play when we want to extend the context. In multiverse type theory, we don't really care. Like the context is very heterogeneous. It just includes a bunch of different types living at different sorts. Whereas in multimodal type theory, since the context has to live in a specific mode, we can only extend the context by also annotating with the type with a modality that brings the type into the mode we're interested in. So you can see that this rule is more complicated than the left one, but it's for a good reason, I'll argue. And that leads to less verbosity for multiverse type theory compared to multimodal type theory, but for the same reason, it can't handle things like non-idempotent modalities, because basically multiverse type theory cannot distinguish. Like if it sees a type coming from S-prop, for example, there's only one way in which it can come from S-prop, whereas in multimodal type theory, you can say, oh, it's been going through types and S-props and types and S-prop or whatever. So it might be trivial for this example, but for guarded type theory, for example, it's not. And the other difference is that in the attempt at multimodal type theory, there is a framework that can accommodate some inductives, whereas in multimodal type theory, there's nothing in place to accommodate them. You have to add them manually. But multiverse type theory is quite complicated. It uses rewrite rules, which is notoriously hard to use and formalize. And also we think that there's a way of translating, because what I was saying before is that basically multiverse type theory is a more trivial system than multimodal type theory. There is a possibility of translating the rules of multiverse type theory into multimodal type theory. So this is one of the reasons why I'm going to concentrate on multimodal type theory afterwards, because I think it's maybe a bit more principled here. But they also share the same shortcomings. So for example, we cannot parameterize S-prop using them because there is no way to just require types at a mode to have some additional definitional equalities. You have to add that on top. They don't have inductive types in general, so you can also add them manually into the framework in multiverse type theory, but there is no general idea of what an inductive type is. And we have full MLTT at every sort or mode, which I mentioned before we might not want to have. For example, if we want to have the interval universe in cubical Agda, it just doesn't have MLTT. And then I'm going to talk a bit about the different implementations that exist right now of those systems. So you have simply tight MTT, which is SYCL, which is what Joris is working on. There's full MTT with Mitten, but I have to say I think that Mitten is less general than MTT because it needs mode theory where basically you only have Posetto, like it's 2 Posetto basically. So it's not the more general version of MTT. There's also Agda, but a very simple implementation. There's only one mode and predetermined modalities. And we also have Cox implementation of type prop and sprop, which is more multiverse-like. And in some way, Agda also has a multiverse implementation because it has prop. So Agda combines both in a weird way. For example, for irrelevance, you have both the choice of the multiverse prop and the modalities of irrelevance. And they don't really communicate. So I'm going to focus on what we might want additionally from MTT in order to have an actual usable type theory in a day-to-day basis. So for example, we might want inductive types, but the question is, do inductive types need to exist at all modes? It's not clear. And are there elimination principles through all modalities? And that the second one just isn't true because of the examples I showed you. And the main problem is that in MTT, we cannot really consider the problem of inductives because since you cannot encode mode-specific behavior, you can't really say that you have inductives because those would depend on the mode-specific behavior. So it's not something that we can consider right now, but that it's something that we would like to consider. So for example, well, I'm giving the examples of bool in sprop and bool in type because those would also be the corresponding inductive types at the specific modes. So this is something that MTT currently doesn't cover, but that you would need to cover if you wanted to implement this in proof assistance. There's also identity types. So for example, MTT has identity types, which are not defined as inductive types. And it has them at every mode. So that means that, for example, if I'm at a mode M and I have one type A, then A equals B is at the same mode M. But it's kind of weird. For example, I gave the example of exceptional type theory. Do we really care about the exceptional equality between 1 and 0? Because, I mean, I could just return rays, right? So is it really the kind of equality we want? Maybe we might want an equality that lives in a single specific sort. For example, sprop, to have UIP, for example. And so this is part of the approach of the observational equality version of Puget and Tabarot. And so this is yet another question of what do we want out of our equality type? And it's not a question that I really have a principled answer for. We might have different justifications for having an exceptional equality. I don't see why personally, but why not? And also universes. I think it's really important also because MTT has universes at every mode, but so that's really important for some systems. So cubical, you really need to have the universe at the same mode because you might want to apply all the cubical primitives to the universe itself. But in the case of sprop, do you really want a universe where all the elements are definitionally equal? Not really, I think. Well, you might have a use for it, but I don't see one personally. And for exceptional, well, you might want an exceptional universe where there's a weird rays type, but maybe there's a use for it, but also maybe there's a use for a universe where you don't have the race type. So you might want both, I don't know. So again, it's not something that's really clear, and we don't really know what we want. And if you have any idea of whether or not the universe in sprop, for example, could be useful, I'd be really interested, or in exceptional. And in all those cases, well, we might want to have sort generic theorems, which means that we don't really want to prove the same theorem in type than in sprop, than in exceptional, or whatever. So we might want to have some mode quantification, but of course that's going to be complicated, so we might want to just have prenex mode quantification. And I put also, this would require quantifying over their interactions. This is, if we do want, for example, to eliminate something into another universe, you'd also have to ensure that some inductive types can be eliminated into some other universe and have to quantify on that, so that's yet another complicated thing. But for example, sort polymorphism kind of already does this. You have basically pre-next quantification over the sort in Coq, and you can write sort generic theorems. And people are working on, for example, proving generic theorems about the equality in Coq right now. And on the MTT side, Andreas gave a talk about at types about basically a type theory for mode theory, where you would be able to, well, kind of quantify and talk about different modes internally. Okay, and I think so. That's the structural framework and what we might want from the structural framework. But now we might also want to prove things about our systems. And the meta-theoretical properties are not even very well defined in a way, because, for example, types in SPROP don't really enjoy canonicity because every value is the same as any other value. Consistency in exceptional, you don't really have it, but is it really consistency? So we already need to identify what is an actual meta-theoretical property we want, and so we might want to have consistency at a specific sort that we single out to be the actual regular sort. Ah, okay. We might also want to have conservativity, so that you can't prove anything new. But even decidability of typing might only make sense at certain sorts, but I don't really know how to write those kinds of properties yet. And yeah, we might want to ensure the transition is painless. Yeah, I'm gonna skip over the last versions to just say what we want at the end. So basically, the idea would be to be able to glue different systems together in a predictable way and not have to redo the proofs that we've already done for them. But this is really ambitious, but this is basically what Umura presented last year at Working Group 6. And we want to be able to formalize this as well, which is kind of complicated. So yeah, this will require solving some complicated engineering problems. So either going Sterling, Gratzer, or Bouquet, Kaposi, and Sattler, which we don't know yet how to formalize completely in Coq and Agda. And we also want to implement those systems in the end in actual proof assistance. So that might take a while, but maybe in 50 years we'll have those. Thanks for your attention. And if you have questions or ideas, I'd be glad to hear them.
Okay. So I think it's maybe just kind of a remark or on a follow-up on the question of what kind of inductive types you want. I think it would make sense to separate universes with crazy inductive types with universes that are more conservative, so that you can separate away. Like if you want to do inductive, recursive, higher co-inductive types, you can. And that's fine, but also you can assure that you have maybe a more conservative universe, which have maybe just like kind of the indexed one that we know have some reasonable semantics, or I mean maybe not so reasonable, but like so that we don't have to kind of force on the semantics that it has to model all the fancy higher things. I think that would be also some reasonable separation to have, and then maybe you can eliminate from the sort with the crazy inductive types to the sort with the normal inductive types only the normal ones, and the other ones that just live in their side, and then you can't really come back. I think that would be also another thing I'd want to separate away somehow.
Yeah. So in some sense, like maybe you've seen Martin Escardo's complaints about this, for example, in Agda, that
No,
he only uses the bare basics, and he wants to make sure that he only uses the bare basics. And Agda, since it allows you to do whatever you want, you might want to have some separation of concerns. Yeah. I think that would be a nice idea.
Yes,
Would answer kind of this question.
You want the mic?
Okay. I mean, I'm not convinced. Sorry, but it seems to be that too much is put into types. Yeah. So I'd like to keep types for what they're for, and not all sort of things which are rather part of the sort of tools chain of the implementation. So I mean, okay, I wouldn't mind if there's a flag in Acta or a cock or whatever. They say I want to stay pure or whatever. But I'm a bit worried, always, to put everything into types. I mean, I'm saying this multiverse stuff is certainly an interesting idea, but I would be cautious not to put things which may be part of the of the tool chain of the user interface, to put everything into types. I'm just a bit worried about this.
What do you mean by part of the tool chain? Is it the exceptional, for example?
Yeah, no, okay, that's fair enough. But I'm just referring to the previous suggestion to have like universes which specify how many features you use, like the Spartan type theory, a la Martin Escardo, and so on. I think that goes a bit too far. So I would just keep it to sort of sensible semantic properties. I mean, obviously, when we do directed type theory, we have to make a difference between the directed and non-directed universes. But so there are different universes that make sense, expressed by these modalities, which should correspond to some semantic ideas, but not to some sort of limitations of how many type formers you want to have. So that I would say is one step too far, to be honest.
Okay. So you mean keeping those kinds of restrictions behind just flags, for example?
Yeah. Whatever. I mean,
Another questions? More questions? Oh. Okay.
So I think that's kind of an answer to that question. It's just that the problem, I think, that, I mean, the point of these like multiverse things is that that of the duplication of work, like that what he said, for instance, for the standard library of Agda, is that you have two standard libraries and they don't talk to each other, and everything is kind of, I mean, okay, maybe they can talk to each other a bit, but I think the problem with flags is that they have this very kind of global thing that prevents you to have things interacting somehow. And I think...
this question of good software engineering, right? I mean, how do you deal with this? You can translate.
But we type theorists. This is like that.
Don't put.
I don't know.
Yeah, you have a hammer and then.
Everything looks like a nail.
Okay, let's there. Fair enough. Ah, wait. Yes.
Okay, so thanks, Josselin. And,